Hello everyone and welcome to AISC's webinar, Drawing and Specification Requirements for Seismic Design, presented by Larry Muir and Tom Sable. Today is July 21st, 2016. My name is Christina Harbour. I am with AISC's Continuing Education Group, and I'll be moderating today's presentation. We have two speakers for today's webinar. Our first speaker is Larry Muir. He's the Director of Technical Assistance at AISC, where he oversees the operations of the technical aspects of the AISC Steel Solutions Center. In addition to over a decade of practical experience with a steel fabricator, he's authored or co-authored dozens of technical papers, presentations, and book chapters on the subject of connection design. In 2014, Larry was the recipient of the AISC T.R. Higgins Lectureship Award. He currently serves on a number of AISC, ASCE, RCSC, and AWS committees. Welcome, Larry, and I'll hand things over to you.
Thank you, Christina. Today we're going to talk about the requirements for the drawings and specifications on seismic projects. And in this presentation, when I talk about a seismic project, I'm talking about a project that has to meet the requirements of AISC 341, which is the seismic provisions. And when I talk about a non-seismic project, I'm talking about a project that only needs to meet the requirements of AISC 360, which is the AISC specification for steel buildings. So with that out of the way, I'm going to give a brief overview, sort of what we're going to be talking about today, primarily what I'm going to be talking about, and then what Tom will, very briefly, what Tom will be talking about later on. So the first thing I'm going to talk about is why do we need this presentation to begin with? And one thing I try to concentrate a lot on in presentations is more the why as opposed to the how, so that there's an understanding as to what objectives we're trying to meet. And then, you know, why do we need to provide the information that we're going to talk about today? What standards apply? What information needs to be shown on the drawings, and then what kind of problems are we actually seeing in practice. And then at that point I'll turn it over to Tom Sable, and he'll talk some about how you can actually accomplish these things, which is very useful information for all the engineers out there to understand how this can actually be accomplished. So first, as I said, we're going to talk a little bit about why this presentation is necessary, and I'll kind of put it into a historical perspective. So about 8 years ago, a similar presentation was given at the Steel Conference, and I gave that with Larry Kloiber. Larry Kloiber was then the chief engineer of Legion Steel. I worked for Surveys Steel at the time, so it was two fabricators really sharing their experiences as to how these seismic projects had been going at that point. So a couple things to realize back in 2008, there were a lot of engineers and fabricators who were not yet familiar with the seismic provisions at all. Pre-qualified moment connections for intermediate and special moment frames were relatively new at that point. And then a big change, a big consideration at that point was that the seismic provisions had nearly doubled in length in the 2005 edition of the provisions. And then also the number of projects that were subject to the requirements of the provisions had increased significantly. So basically all that means that there were a lot of fabricators and engineers dealing with a lot of new requirements and trying to get their feet wet on these things. So 8 years ago as well, what we were finding was that engineers' drawings and specifications were often lacking even very basic information. A lot of times there was virtually no way for a fabricator bidding a project to realize that the seismic requirements were in play on some of these projects. And as a result, what we were seeing was that the final cost of some projects were actually multiples of the bid price, and that could be explained by the fact that the fabricators were bidding a project that was very different than the project the engineer ultimately wanted to have built. Because of those seismic requirements, and in a lot of cases weren't being shown. And then another problem that came up, if you go back and I think listen to some of that presentation, which I think is still available on the AISC website, the connections were often required to resist the expected strength of those ductile elements that were intended to be the yielding elements in the structure. But the engineers may not have totally understood the capacity design, capacity related design concepts, and so therefore they weren't designing those other members to resist those forces. So you had connections that were held to a much higher loading standard than the rest of the structure in some cases, and you end up with a lot of reinforcing, and it was difficult to figure out when that reinforcing should end or whether that reinforcing was necessary. And that was really the big problems that were occurring about 8 years ago. So we fast forward to today, and engineers and fabricators are a lot more knowledgeable about the seismic design requirements now. They've had a number of years to get used to them. Another big difference now is that the seismic provisions have stabilized. Jim Malley, who's the chair of TC9 that oversees the development of the seismic provisions, sort of made the statement that the seismic provisions used to be sort of in their infancy, and now they're kind of the young adults. So they've matured quite a bit. They've stabilized. We're not seeing a lot of new requirements. And so that might lead you to believe that all our problems are behind us and there's no reason really to talk about this subject at all. Obviously, that's not the case. We're still seeing some issues. There's still people who are, need to understand what these requirements are and how to fulfill them. And so that's what we're going to try to do here in the presentation today. So continuing with the why do we need to provide all of this information? So the big issue, and I think engineers understand this part of it for sure, is safety. So as an engineer, we don't actually build buildings, we don't weld, we don't bolt things together. We're not fabricators or erectors, but what we do is we produce information so that those processes can continue. So we produce primarily drawings, and then we supplement those with our specifications. And if we want the building that actually exists in the real world to reflect what our intent was and all that work we put into our designs, then we have to make sure we convey that information accurately and clearly. And so we're not going to talk a lot about safety today because I think engineers have a pretty good handle on why we need to design safe structures and fabricate and erect safe structures. But another reason we're going to have to provide this information revolves around money, and we're going to spend a little bit more time on that. So the first thing I want to make clear is that meeting the seismic provisions increase the costs of the project. So this is could be more generally stated that any time you add some requirements to a project, you're potentially increasing the cost of that project. So you always want to keep that in mind. Second point is, and we'll talk about this in a little bit more detail in a moment, but fabricators bid what they see. Essentially, that's what they're supposed to do when they get a set of contract documents. The Code of Standard Practice instructs them to bid what's in those contract documents, and it instructs the other parties, the owner's representatives, to ensure that all the information that's required is reflected in those contract documents. So if there's something that's not in the contract documents that's going to be required on the project that gets caught at some later point, may have been overlooked earlier, then that's essentially a change in the scope from what was established in the contract documents. And when that sort of thing happens, you can expect to see some modification in the contract price and potentially some modification in the schedule as well. And again, that's stated in the Code of Standard Practice, so that's a well-established fact that that's the way that's to be handled. Now, the idea that these seismic requirements have some cost associated with them is sort of reflected in this graph. This is kind of an informal graph. I wouldn't read too much into it. But the basis of this graph was that there was an engineer in the Northeast who wanted to see what the cost impacts were for various seismic systems. And so he took a building and he designed it using various systems, brace frames, moment frames, R=3 systems that weren't specifically detailed for seismic resistance, and then he put them out to bid with a handful of fabricators to see what the differences in costs were and kind of distilled all that information. And so as we would expect, as we increase our R factor, we're decreasing our base shear, we're decreasing the force that's going to be seen by that structure, and so overall the force has been reduced, and some people might think that would result in a more economical structure. But in fact, all the detailing requirements that we have to ensure that these things behave ductilely with all this inelastic behavior going on can increase the cost of the structure. So we can see, just roughly for this one structure that was looked at an R=3, if we move all the way up to an R=8, like in a special moment frame, we could see 2.5 times the cost. And so you can see immediately the problem that occurs, that if the requirements aren't clear, then the fabricator could potentially end up bidding a job for a fraction of what it's actually going to cost him to fabricate and then to erect this project. So that brings us to the dilemma that the fabricator is going to, or the contractor, the fabricator, and the erector both are going to face potentially if you have incomplete contract documents. So they have to make a decision. So they know there's some seismic requirements on the project. They may have a feeling that not all of the requirements that are in play are reflected in the design drawings and the specifications, but they still have to bid the project. So they either bid what they see, which is really what the Code of Standard Practice would tell them to do, knowing that at some later point there's going to probably be additional requirements placed on the job, and there's going to be some cost and scheduling issues with that, and then they're going to have to fight those battles to get paid for the work that's actually required. And again, that's a change in the contract at that point. Or they could try to bid what they think the engineer is going to ultimately want. The problem there is that that's going to increase the cost of the project, and it's going to increase their bid price over relative to the other contractors who have bid the project. And what it really does in a lot of cases is it puts the probably in what would in some cases maybe be the most capable of the contractors at a disadvantage. They're sort of being penalized for their knowledge and experience in this area. And so what fabricators are going to tend to do most of the time, and what they probably should be doing, is bidding what they see. But then that's going to cause some anxiety down the road as those new requirements are put in place, and they've got to battle that through. So what standards apply to these seismic projects? So this is a list. The first thing I want to point out, and it is a point of confusion sometimes, we see at the Solution Center, the seismic or the specification for structural steel buildings, AISC 360, applies to all projects, whether they're seismic projects or non-seismic projects. So you could kind of look at the seismic provisions, AISC 341, as a supplement to that for these systems, these structures that have to be designed for higher seismic demand. But you have to meet both of those documents, the requirements in both for all seismic projects. Then the Code of Standard Practice, which we've already talked about a little bit, applies, and it forms the basis for most structural steel construction projects in the U.S., and it applies equally to seismic and non-seismic projects. There's AISC 358, which contains the pre-qualified connections for special and intermediate moment frames, and we'll talk a good bit about the implications of these pre-qualified connections later on in the first half of this presentation. Then we've got a couple welding codes. So we've got AWS D1.1, which is a structural welding code that applies to all projects, whether they're seismic or not. And then we've got a seismic supplement to that, which is AWS D1.8. So again, on a seismic project, you have to meet both those codes. And then we have RCSC specification for structural joints using high-strength bolts, and that applies to both seismic and non-seismic projects, and there is no seismic supplement for the bolting specification. So what information needs to be shown? I'm going to go over briefly in some parts of this what needs to be shown on these drawings. I'm going to leave a lot of the details to the second half of the presentation that Tom Sable is going to talk about, where he can illustrate these as he lists them. But again, whether you're talking about a seismic or a non-seismic project, the Code of Standard Practice applies. I'm going to be talking a little bit about some differences between different connection design methods that can be used or can be designated on projects. And so I'm going to give a little bit of an overview here of what's possible. So there's three options given in the Code of Standard Practice. All of these could be applied to both seismic and non-seismic projects. Options 2 and 3 are probably a little rarer on seismic projects. However, I personally have been involved in projects where all of the connection design has been delegated, even where there's a high seismic requirements. So the first option is that the engineer of record completes all of the connection design and shows it on the structural design drawings. So essentially everything's engineer mandated at that point. The second option is that the connection can be designated to be selected or completed by an experienced detailer. So the detailer is kind of choosing connections. This would be most common with shear connections. They're left for the detailer to select from the tables in the AISC manual, so a very low level of, I don't even know that you can call it engineering design at that point, but they're selecting connections. Then option 3 is really truly delegated connection design, where it's delegated to a licensed professional engineer working for the fabricator. And so regardless of what connection design option is actually used on a project, there are certain things that need to be presented. So any permanent bracing that's required, reinforcement that might be required, openings and other special details all need to be shown. Another thing that's going to occur, whether we're talking about options 1, 2, or 3, is there's going to be an approval process. And in my mind, the approval process really goes back to making sure we satisfy that safety requirement. So as engineers, we need to clearly and completely show the requirements for the project in the contract documents, the design drawings, and the specifications to make sure the contractor can figure out what our intent is. But then ultimately the approval is that check to make sure that our intent has been conveyed properly and interpreted properly by the contractor. So we every once in a while get some questions where people want to sort of skimp on the approval process, and I would recommend against doing that, and doing so is not consistent with the Code of Standard Practice. But if you choose options 2 or 3 where you're delegating the connection design in some form, then the Code of Standard Practice puts some additional requirements on. So any restrictions on the types of connections that can be used need to be clearly shown in the contract documents, and this is so important on seismic projects, in fact, that you'll see we restate this a couple different times in the various documents. Then if you're going to design connections, you have to have the forces that they need to be designed for. It needs to be clear whether those forces are given at service load or factored load levels. You need to designate whether the connection design is to be performed using LRFD or ASD design methods. And then finally, the engineer needs to inform the contractor as to what substantiating connection information is going to be provided, so that, you know, what we're talking about there is are you requiring calculations to be shown for all the connections, sample calculations, so on and so forth. What exactly are you expecting to see to justify the connection design? Then Section A4 of the seismic provisions contains a list of requirements. As I stated earlier, I'm going to leave a lot of that listing in detail on this list to Tom Sable's portion of the portion of the presentation that will occur later. But I am going to briefly talk about some things related to AWS D1.8, which again is that seismic supplement to the welding code. And so if you look at D1.8, what you're going to find is that there's a restating of a lot of those requirements that are in A4 of the seismic provisions. And where these things are restated, it's where they apply directly to the needs of the welding, the design of the welds, the welding process. And so there's not complete overlap, but there is a good bit of overlap. And so here we see 8 items. I'm not going to go through these in detail for the sake of time. There's another few there, but I'm going to concentrate on item 13 for a minute. So it says that the engineer needs to show joints or groups of joints in which the specific assembly order, welding sequence, welding technique, or other special precautions should be designated and submitted to the engineer of record. One thing I've seen is that some jurisdictions have gotten very deep into what they're requiring in terms of welding, so requiring certain processes, certain sequence of welding, that sort of thing on some of the joints. And I would recommend, for the most part, that the engineer of record, unless they have some very good reason and very deep knowledge of the welding process to require something specific, that they leave these decisions to the fabricator. I worked for a fabricator for a number of years. I probably have a little bit more knowledge than a lot of engineers about welding and fabrication. But even with that little bit of extra knowledge that I have, I would leave those kind of decisions to the guys on the shop floor who really have the knowledge about these things and are going to have to ultimately pay the price if they end up with cracking of welds or whatever during fabrication. There are a couple things in AWS D1.1 that are not addressed in Section A4 of the seismic provisions. So these are additional requirements that might get missed if you were just looking at the seismic provisions. So the first item is the engineer shall include a quality assurance plan for the project. Primarily that quality assurance plan is going to probably may wholly just reference chapters N of the specification and chapter J of the seismic provisions. But if you have any additional requirements beyond those, then you'd want to make those clear as well. And then finally, any additional project-specific provisions not governed by AWS D1.1 or 1.8 that you're going to enforce on your project need to be clearly shown. Again, unless you have some very deep knowledge of welding and some very specific reasons you need something different, you're probably just going to want to adopt the requirements of AWS D1.1 and 1.8 directly rather than adding things to that. I also want to point out that even though a lot of engineers probably don't have the AWS documents readily available at their desk, or maybe potentially even in their engineering office, AWS D1.8 does provide a pretty good reference for engineers related to these issues, because when they list these requirements that need to be shown on the engineer's drawings, they provide a cross-reference back to what the requirements related to the actual process of the welding are within AWS D1.8. And where this could come in handy is if an inspector is saying that the contractor's done something that's not complying with AWS D1.8, or you have some question from the contractor themselves about what they should or shouldn't be doing, you can go directly into that list, see what you've required, and then go into the more detail in the subsequent sections and try to see whether what they've actually done matches what was intended or not. So it's a pretty handy resource in that way. I'm going to talk a little bit about what problems we're actually seeing, and as Christina mentioned in the introduction, I'm the Director of Technical Assistance for AISC, which means all the questions that come into the technical questions that come into the Steel Solutions Center at some point go through me. Either I answer them or I'll review them before they're actually sent. And so I'm pulling the information in this next section directly from those questions that we're seeing at the Solutions Center. Some of it also reflects what I saw in practice relative to these seismic projects and what some of the concerns were and some of the problems were. So a big issue, we're not going to spend a lot of time on it, even though it's probably one of the biggest issues facing structural steel construction overall, involves incomplete bid documents. This applies whether we're talking about a seismic project or a non-seismic project. We already talked about why we need to have complete and accurate bid documents and construction documents to ensure we have safe and economical structures, but we all recognize as well that we get into sometimes these fast-track type projects, and there's not a lot of time. Sometimes we don't have all the information we need, but it's important to really concentrate on making these documents as complete and accurate as possible, just to avoid all kinds of headaches down the road. Now, beyond just incomplete documents, here's some common issues that we've found. So the first one, I've kind of grouped some things under the heading of imagined requirements. So these are three specific examples of imagined requirements, but this comes up pretty frequently at the Solutions Center, where it could be an engineer, sometimes it's an inspector, sometimes it's a fabricator and an erector, believes that something is required by the seismic provisions or sometimes even the specifications when there is actually no such requirement. So one of the big ones that comes up is the belief that all steel must be 992 or even that all steel must be grade 50 if you're designing a seismic project. And there is no requirement for this in the seismic provisions. And in fact, if you go into AISC 358 with the pre-qualified moment connections, you'll see references where we specifically allow A36 steel to be used on plates or grade 50 steel to be used on plates other than 992. And the plates and angles and some of the other connecting material probably is not going to be available in A992. So requiring all steel to be 992 on your contract documents essentially means that no one will be able to build the project that you've outlined in your contract documents. The next two items there, the demand, sometimes people believe that all the welds on a seismic project or all the welds within the seismic force resisting system must be demand critical. That's not true. We'll talk about that in a little bit. And then all backing must be removed is also not true, and we'll talk about why backing is sometimes left in place in a moment. And then connection configurations desired but not defined. We'll see that in a little bit. This goes back to the Code of Standard Practice as well, where any restrictions on the connection configuration needs to be shown. And then finally, we'll talk a little bit about pre-qualified connections and some of the problems we see related to those. So talking about demand-critical welds, generally demand-critical welds are required where you got these high ductility systems where you're going to get a lot of inelastic behavior. So we're talking about groove welds at column splices and bases at these higher ductility systems. So we see there the intermediate moment frame, special moment frame, special truss moment frame, the special cantilever column systems, special concentrically braced frames, eccentrically braced frames, buckling restrained brace frames, and the steel plate shear wall systems. So what we're seeing there are references to intermediate and special systems, so higher ductility systems. And then the groove welds at beam to column connections in higher ductility systems as well. So again, the intermediate and special moment frames, and then the special concentrically braced frames, the eccentrically braced frames, and the BRB brace frames. Now it may seem odd to talk about beam to column moment connections in those brace systems, but there are options which would allow you to choose to use a moment connection to satisfy some of the requirements of those systems. And when that happens in these higher ductility systems, you're going to need demand critical welds. Generally, demand critical welds are not required for lower ductility or ordinary systems. So they're not required in ordinary brace frames, for instance, or ordinary cantilever column systems. It's nice when you can sort of pigeonhole things pretty easily. So if you had a high ductility system, you need demand critical welds. If you have a lower ductility system, you don't. In this case, there is an exception. When we're talking about the groove welds at beam to column connections, even if you have an ordinary moment frame, those welds are still going to be required to be demand critical, and the demand critical requirements are laid out in AWS D1.8. So one thing that comes up sometimes at the Solution Center is somebody will ask, why, am I required, the engineer says this needs to be a demand critical weld. Do these welds need to be demand critical? And they could be talking about welds to gusset plates to beams, or in any number of cases. And what I'm suggesting here is a simplified conflict resolution. When you go into the seismic provision, our intent, just like what your intent should be when you write your contract documents, our intent is to be clear and accurate in the information that we're providing. We're not trying to hide any requirements. I don't believe there are any hidden requirements or very vague requirements in the seismic provisions. So in terms of demand critical welds, if you want to figure out whether something needed to be a demand critical weld or not, the simple process is simply to open up the PDF of the seismic provisions, which you can download for free from the AISC website. Press Control F to open up the Find feature, type in the term demand critical and hit enter, and it'll bring up everywhere a demand critical weld is required in the seismic provisions. So that's a very easy way to resolve those kind of disputes. Next, I'm going to talk about removal of backing. So this one actually comes up a lot from fabricators and erectors, more so even than from engineers, where a fabricator or erector believes that all backing needs to be removed as soon as they're having to meet AISC 341, the seismic provisions. And that's not true at all. You don't, in the majority of the cases still, you can probably leave your backing in place. In some cases you're going to need to reinforce it, and we'll talk about that in a minute. But to try to understand why we have these requirements, I'm going to go through the next couple slides. So you put backing in there, and you're going to notice that we're talking about a T-joint here, and we'll talk about a butt joint in a moment and the difference. But you put the backing in place, and a couple things happen here. There's going to still be some stiffness at that backing, which when you have stiffness, you're going to tend to draw stress towards that stiffness. And so you're going to try to draw some stress. You're going to tend to draw stress into that backing bar. And then there's some lack of fusion right there at the backing bar because you're not CJP welding the backing to the column generally. And that's going to potentially cause a stress riser. So you have stress going to an area where you sort of have an inherent crack, and that's the reason for the concern when you've got these large inelastic deformations going on in the structure. And ultimately that could lead to some sort of rupture there and maybe some propagation through the rest of the weld and a loss of a joint, which is going to, obviously something nobody wants to have happen on these projects. So that when that's a concern, we've got a couple different options. So one is if you're at the top flange of a typical moment-connected beam, or more generally, the idea is if you're towards the inside of the section with your backing, then you can provide a contouring fillet and leave the backing in place. And that fillet will tend to bridge the gap where that incomplete fusion is there, and it just sort of generally provides a better stress path through that backing. So that's one option. Then the second option is when you're towards the outside of the joint, so we're talking about like the bottom flange of a moment-connected beam, we require that the backing actually be removed, and then you have to remove the backing, back gouge, and then provide a smooth transition at that area, again, because you're going to be pulling stress in there, and you may want to make sure you got a smooth load path or stress paths, and you want to not have that discontinuity there. And part of the reason for the difference between the top flange and the bottom flange requirements is based on what we've observed from the test. It's a better condition at the top flange. It's less of a problem there with cracking. Now, both those instances were T-joints. There's also cases where we have a butt splice like we're showing here with a CJP weld. And in cases like this, the stress path is pretty smooth and pretty clear, and there's not the same kind of tendency, even though there is still some stiffness of that backing, but there's not the tendency to have the stress try to enter the backing and then come back out of the backing on the other side of the joint. So we have less concern. So generally, we don't require, I don't think there are any requirements in the seismic provisions to remove backing where we have a butt joint like this. So with a column splice, there's no requirement. And engineers are free to require, demand critical welds or removal of backing or contouring in other locations beyond what's in the seismic provisions. Again, I would recommend, unless you have some very good reason to do so, that you should probably just stick with what the requirements are as written in the provisions. But if you decide you need to add these additional requirements beyond what's in the specification or what's in the provisions, I would say go the extra mile to try to make sure that those are very clear and that they're highlighted in some way, because whether we're talking about a seismic project or a non-seismic project, one of the issues we do sometimes run across is where there may be a requirement in the contract documents, but maybe it got buried somewhere and nobody really picked up on it until late in the project, and it can cause some problems. So the fabricator may have missed on the front end. The engineer of record may have missed it, in the review of the shop drawings, and now you're well into erection in some cases, and it gets picked up. So it just is to everybody's benefit if you try to highlight anything that's unusual to the best of your ability. I mentioned that the Code of Standard Practice has requirements that the engineer list any restrictions that they put on the type of or configuration of connection details if they're delegating connection design. Section A4 reiterates that, and then D1.8 also relative to welding reiterates that sort of requirement. Where it comes up a lot is, again, it almost falls under those imagined requirements. So this is just an example. There's other examples that could be used, but for time I can only really hit on one thing. But when you have a braced frame, you have to accommodate the inelastic behavior of the brace as it buckles. And there's many ways that can be done. The requirement is that it be accommodated in some manner. The most common way probably to do this in our industry is shown in the upper left there. And it's just to provide that 2T bend line or fold line or whatever you want to call it. And that's certainly an option, and it's very common. However, you need to recognize it's not the only option. So right below that, there's a detail with a hinge plate, where rather than having the out-of-plane motion being accommodated in the gusset itself, it's handled in that splice plate. It's very similar detail, but a little bit different configuration. And then there's also an option where you get it if the brace is going to buckle in plane of the bay. Then you can actually develop there's a requirement to develop the expected flexural strength of that brace, accounting for strain hardening. So that's the 1.1 multiplier there. And any one of these connections that are shown could be used to satisfy the requirements of the seismic provisions. If as the engineer of record you're delegating connection design, but the only thing you're going to accept is the 2T on the brace, then you should make that very clear that that's what the requirement's going to be. Otherwise, the fabricator or the contractor should be free to choose whatever is going to be most economical for their work. Now, the last item we see come up fairly frequently, I'm calling it public enemy number one here, because it does seem to cause, it comes up pretty frequently, but when it comes up, it does seem to cause a lot of headaches for people. And it has to do with the pre-qualified moment connection. So if you're designing a intermediate or a special moment frame, then the seismic provisions require you either to have, they require you to have physical testing essentially on these connections. So that can be accomplished either by having a pre-qualified connection out of AISC 358, or you would have to physically test run your own testing program essentially on these details to make sure you satisfy the requirements that are laid out in, I believe it's Chapter K of the provisions. And so the big thing here is before you get too far into your design, and certainly before you get into the construction phase, you want to ensure that there exists some pre-qualified connection that will work with the structure that you've designed. And to kind of highlight the problem, I'm going to go through some specifics of where we run into these problems a lot. People don't understand that there aren't pre-qualified connections. And then we'll go into a specific configuration and see what the limitations are on that. So first off, big item people sometimes miss is that there are no pre-qualified connections in AISC 358 that frame to the weak axis of a column. If you have orthogonal framing at a common column with moment frames, you can sort of get around that problem because AISC 358 has some built-up sections that can be used to essentially provide 4 flanges around the column. So they have cruciform sections, they have box sections, they have plated wide flange sections, and so that's an option. But simply framing to the web of the column is not an option. Another thing that sometimes we get questions about is if these column sections, these built-up sections, are assumed to be prismatic, so you can't just provide the reinforcing or that section over a small length of the column. It's intended to be over the entire length of the column. Another area we get a lot of questions about, a lot of problems, is with HSS. So your options are fairly limited with HSS in terms of pre-qualified connections. There's only one pre-qualified option for HSS columns, and those columns need to be concrete filled. There's only one pre-qualified option for HSS beams, and then there are no pre-qualified options for HSS columns and beams used together at the same joint. So that's something that's often missed. Now, if you can use an ordinary moment frame, then that's a good way to use an HSS. That's a good option. When you get into these special and intermediate moment frames, you can run into a lot more problems there. Then again, this is just an example. I'm picking in a reduced beam section to highlight the fact that each of the connection types in AISC 358 have pre-qualification limits associated with them. So sometimes what we see is an engineer will choose columns and beams and then sometimes they'll designate a connection type that may be included in 358, or sometimes they'll leave it completely up to the decision of the fabricator. But then it turns out there are no pre-qualified connections that will meet the requirements. And so your option then becomes having to do some kind of physical testing program, which would not fall normally on the fabricator and would not be included in a bid price. I think it's reasonable for a fabricator to assume that the engineer has designed his structure so that there are pre-qualified connections that can be used. So relative to the reduced beam section, there's a number of limitations on the beam sizes. So you have to have a rolled wide flange or a built-up I-shaped member. So again, that goes to the HSSs. There are no HSSs, reduced beam sections, which is probably clearer for the reduced beam than for some of the other configurations. But there's limits on the depth, there's limits on the weight, there's limits on the flange thickness, span to depth ratio, width to thickness ratios for the flanges and webs. There's lateral bracing requirements, which also sometimes become difficult to meet and sometimes get overlooked in the early stages. And then there's protected zone requirements. And then if we move on to the columns, we're going to see we have some limitations there. Again, we got rolled shapes and built-up sections, so they're generally not HSS for a lot of these systems. The depth limits are there, and there's different restrictions for built-up members as well. Width to thickness ratio for the flanges and webs again, and then lateral bracing requirements for the column itself. And so if you want to go through each one of those items as you're designing your structure and make sure that you can find a connection that satisfies each of them. And so for each configuration, each connection type in 358, it's going to have its own set of limits. You want to make sure at the start, before the start of construction, at least that there's a pre-qualified connection for your project, because you certainly don't want to find out, after construction starts, after everything's been released for construction, that you got to do some sort of testing program or do a lot of backing up through your calcs to resize members and that sort of thing. So with that, I'm going to turn it over to Tom Sable to talk about how you actually get all of this information onto your contract documents.
Okay, actually, I'll introduce Tom real briefly. Sorry. Our next speaker is Tom Sable. He is a principal at Engelkirk, a Los Angeles-based firm specializing in structural and earthquake engineering. In addition to his work at Engelkirk, he serves on a number of research and standards development groups, such as AISC seismic provisions and specification committees. And in his spare time, Tom is an adjunct professor in the Civil and Environmental Engineering Department at UCLA, where he teaches graduate and undergraduate courses on earthquake engineering and structural steel. Welcome, Tom.
All right. Well, thank you. Larry, I think, did a very comprehensive job of trying to explain the reasons behind the requirements. And as he suggested, I'm going to spend a little bit more time talking about how these things might be accomplished. And so the focus that the seminars had up to this point has basically been with respect to steel, and that's not surprising given that it's AISC that's sponsoring the webinar. But I also want to talk a little bit about some of the things that are required in the building code that relate to information that needs to be shown on the drawings themselves. The building code, and let's say the IBC, for example, basically has a focus on things like the seismic design parameters and quantities such as base shear, inspection requirements, and structural observation requirements. And these are typically triggered more often in projects that have a seismic component in them. The AISC standards, on the other hand, and AWS, focus basically on system identification or detailing and the material requirements that are most appropriate for the seismic projects. Now in the IBC in section 1603, they list the following information that has to be shown on the drawings, and I think one of the things that's overlooked frequently is that this information needs to be shown even if seismic does not govern the design. So things such as the risk category, which used to be called the occupancy category, seismic importance factors, two factors that appear to be similar but in fact are different. These are the mapped spectral response parameters. These are the ones that are more or less normalized for a certain site, and then the design spectral response parameters that reflect the individual characteristics, at least to some extent, of the particular site at which your project is located. And so these are required to be shown in both, or both of them are required to be shown. Then things such as the site class, that is, gives you some sense of what kind of soil, and then ultimately the seismic design category, which is important in terms of determining whether or not a project must follow the requirements for AISC 341, or if there's the option of trying to resist the seismic forces by using a requirement, or following the requirements only in the main specification, but having to design for a much larger seismic force. In addition, the IBC, for example, requires that the seismic force resisting system be identified. It's very difficult for a fabricator to look at a drawing and see that, oh, there are moment frames or a brace frame, and know whether or not that's a special or an ordinary frame. They want to see the design base shears, seismic response coefficients, the R factor, and the analysis procedure that's been used. So as an example of how that information might be shown on the drawings, these are just some examples. And throughout the seminar, I have various examples that show how the information can be shown. This is not the only way, and probably most importantly, we're not trying to advocate that details should be done the way they're shown on these slides. They're more for just general information. But you can see, for example, the mapped spectral response factors, the design factors that are used, and then some of the quantities related to, for example, design base shear and what the response coefficient is. There are two things that are shown here that are not required, and that would be the redundancy factor, and that can become important in terms of determining some of the demands on individual members, as well as the maximum drift ratio per floor. And that can be useful information if your building has a curtain wall system and the curtain wall subcontractor needs to know what kind of deformation their system needs to be able to withstand. Within Section 1704, it addresses basically the idea of inspection, and in Section 1704.3, it addresses the issue of special inspections. Now, the IBC makes it convenient, rather than imposing a whole set of separate requirements, basically defers to AISC 360 in Chapter N and AISC 341 Chapter J for the inspection requirements. The AISC 360 requirements basically apply to all steel construction and have an influence on the seismic requirements. 341 Chapter J speaks specifically about the requirements for inspection related to seismic systems. There's a little bit of overlap, but in the last revision to both documents, I think there's been a much better marriage between the two, although there's still some harmonization that's going to have to occur. And then in Section 1704.5, the IBC also addresses the issue of structural observation. And I wanted to draw a distinction between structural observation and special inspection. The idea behind structural observation is that it obligates the designer, most commonly, although another design professional can be designated as a structural observer. We don't see that happen very often, but it is permitted. And the idea is that the structural observer is the one who understands what is the underlying design intent behind the entire seismic system and how that information has been shown on the drawings, so that when the structural observer goes out, what they're really focusing on is, has the contractor and the inspector correctly interpreted the design intent of the engineer of record. And as a result, very often it focuses on kind of the first time things happen. And so what I want to do is just take a look at how some of the special inspection requirements might be communicated, as well as how that information related to structural observation can be communicated. So here's an example of a list of inspection requirements that are required by Section 1704, and the engineer has listed what the items are that need to be inspected and whether or not the inspection is to be conducted continuously or in a periodic manner. And most of this information would be derived from a review of AISC 360 Chapter N and AISC 341 Chapter J. And as I mentioned at the bottom, that was just a partial listing. In particular, the building code requires that if a project has seismic detailing requirements, that those inspection requirements be specifically listed. And so here is a listing of some of them. The majority of the seismic inspection requirements have been referred to through reference to AISC 341 rather than repeating the same things that are already, I think, fairly clearly presented in Chapter J. As I mentioned, the structural observation basically is trying to confirm that the contractor understands and the inspector understands what the intent is of the engineer of record. And so you'll see here that there's an emphasis on the first time a particular thing might occur. For example, the first of the special moment frame connections, so that they go out there, they look at them, and then the assumption is, and then the inspector can enforce it, that they have understood what was intended, and those things can then be constructed without having the structural observer having to come out time and time again to review basically the same thing. There are jurisdictions that have chosen to overlook the intent behind structural observation and are requiring, or at least appear to require, the structural observer to come out every time something is done. So every time there's a placing of rebar in the metal deck and concrete slab that has drag bars or cord bars, they're saying, you need to come out and look at that. And technically that's not required. Now whether you want to fight the building department on that, is something that you would have to decide based on your own project requirements. In 341, as Larry indicated, there are some things that are required to be shown on the drawings. And they have been broken up into kind of general things, as well as more specific related things that we'll come to in a moment. And rather than go through all of these different elements, what I want to emphasize is kind of the rationale behind why this information needs to be shown on the drawings. The engineer of record is the person in the best position to be able to identify the elements that are in the seismic system. Sometimes it's very easy to see, and as we'll see when we look at frames, for example, it's pretty obvious, okay, those are part of the seismic system. But then how the frames are connected to the balance of the structure, it's not necessarily obvious. And that's some of the information that needs to be shown. Larry also indicated the issues with respect to demand-critical welds and protected zones and things like that. Again, it's the engineer of record who is probably in the, well, I'd say not even probably, is in the best position to be able to identify those items. Then as it relates to steel construction, the configuration of the connection, whether or not it's being designed by the engineer of record or delegated, is something that needs to be shown on the drawings. And so I'll provide some examples of that. Larry talked about demand-critical welds. I think he may have been a little kind in his explanation of why sometimes drawings show all the welds as being demand-critical welds. My experience is that sometimes engineers just get confused and they throw up their hands and they say, well, I can't figure out which ones are supposed to be demand critical, so we're going to make them all demand critical welds. And while the engineer has that prerogative, that's not, I think, a very good use of the owner's money, because not all welds need to be demand critical. And the seismic provisions are specific about the ones that they have identified that should be demand critical. lowest anticipated service temperature is one that most buildings don't have to worry about, but it can be an issue with respect to some of the facilities, let's say an industrial facility or a facility that is going to be constructed in a cold weather environment and is not going to be protected from that environment. The idea of the 50-degree Fahrenheit limit, above which you don't need to worry about it, you can just rely on the basic requirements, is really to identify the things that are what we might consider to be conditioned environments. And so in these colder environments, there are some provisions that need to be made, and so the engineer of record, again, is the one who is required to make that designation. And some of these other items I will illustrate through some of the details, and so I won't go through them in this. Larry has already talked about them a little bit. The last one, item 13, joints or groups of joints in which a specific assembly order or welding sequence or whatever it is to be specified, and that information needs to be provided to the engineer of record. Also might refer to some of the things where the engineer of record has elected to require things that are not specifically designated in the seismic provisions. And there may be, as Larry indicated, some very good reasons to deviate from that, but I think it represents something that the engineer has to make a conscious decision rather than simply, again, throwing up their hands and saying, well, we're going to require that everything be something or other. And then the last category is for composite construction. I'm not going to talk as much about that because it's not as common, but just to point out that there are requirements in terms of what must be shown on the drawings that are specified in Section A4 of the seismic provisions. Now there are many ways to accomplish the requirements or to satisfy the requirements that I have just talked about. And so I'm going to present at least a general strategy that you might think about. Different firms, when they're designing seismic projects on a regular basis, probably have developed something that they have found works effectively. Those who are doing projects for the first time might want to give some thought as to how they can simplify the communication of the seismic specific information, achieving a high level of consistency as well as clarity. And so one of the things that the many engineers have found is that grouping the seismic specific information on separate seismic force resisting system sheets, or SFRF sheets, really can simplify things by a large degree, because then it's clear to everyone that this is where the special detailing requirements, things that relate to pre-tensioned high-strength bolts or some of the other requirements related to welding apply. And in the general notes, you can define what the seismic force resisting system is. And then use typical details to present the repetitive information, and in that way avoid inconsistencies. One of the things, though, I'll point out is that the great strength of the typical detail is that it does provide this level of consistency. On the other hand, there can be a great temptation to assume that a typical detail applies to a project when it actually doesn't. And so you need to make sure that you modify those for the specific requirements of your project. And then identify the conditions that require specific detailing. And again, in this way, spend the time to treat the things that are specific to your project, whereas the things that are typical, you can kind of get some return on your investment for the amount of time that was spent developing the typical details in the first place. So again, the requirement to show what the basic seismic force resisting system is both a requirement in the IBC, or the building code, as well as in 341. And this example illustrates the fact that you may end up with more than one system, either vertically or in the horizontal directions. And so in this case, there may have been a superstructure and a substructure, two different lateral force resisting systems. Larry mentioned that ASTM A992 steel is not an absolute requirement for seismic systems. It's generally recommended as the primary choice for wide flanges. It has some desirable quantities from a seismic performance perspective in the sense that the maximum yield strength is limited, whereas with some of the other ones it's not. Now we try to address that fact in some of the design requirements using the expected strength factors. But we also have the option of specifying other grades of steel for different functions. And so you can see these here. One point I want to make with respect to the anchor rods is that generally speaking, we try to use the lowest grade anchor rods that we can rather than specifying a single grade unless that lowest grade works for everything. But what we find is that for gravity systems, either the grade 36 or grade 55 usually work. But for the seismic, we often find ourselves having to rely on the grade 105. And we try to be very careful about where we specify those because it is difficult, in fact it's not possible to weld them. And so if something is placed in the wrong position, one of the anchor rods is placed in the wrong position, it can be very difficult to correct that problem. And so we try to limit where we specify the grade 105s. On the plans, usually it's pretty easy to try to designate what the seismic force resisting system elements are. And so here, for example, the special moment frames have been identified in plan, and I've tried to highlight them with the red rectangles. But also mention that there's a reference to frame elevations that then refer you back to the seismic force resisting sheets, where all the information that's shown on there relates just to the seismic requirements. So here's that elevation. We'll see it becomes a little bit more of a challenge to try to identify the other elements that are part of the system, and that's the reason why I think it makes the most sense to have the engineer of record do that. I mentioned earlier that it can be helpful to group this information on these seismic force resisting sheets, and usually we and other engineers specifically identify them using something like SFRS, and again in your general notes identify those as sheets that are referring to the seismic force resisting system. This drawing shows the basic seismic system in red, and then all the other elements that have been identified by the engineer of record as being part of the seismic force resisting system. Now most of these members are the drags or collector members that connect the rest of the structure to the seismic force resisting system. As you can see in this building, it's not necessarily very seismically friendly with that nice big opening in the diaphragm, and the fact that all the frames ended up having to be located in the upper portion. And so there were a fair number of elements that were designated. In addition, there are also bracing requirements, and I'll show that in just a moment. So here is an example of how the connections that relate to the seismic force resisting system might be indicated. Again, a fabricator looking at a gravity cantilever beam, or a beam that, for reasons of deflection control, for example, the engineer decided that he or she wanted to make it a moment connection, would not have a very easy time trying to differentiate that from a seismic connection unless the engineer makes it explicit. And so here, for example, the engineer has specified a gravity type moment connection, but using CVN filler requirements in order to have that member act as a drag member. This connection down here is a seismic specific detail that again is defined in a legend that the engineer has included on the plans, and there are probably other symbols that would have been included. I just condensed it to show the ones that are related to the seismic force resisting system. So here's the one, for example, that looks like a regular moment connection, but also needs to meet the Sharpie V-notch filler requirements for the seismic force resisting system. And then an example of what that specific SFRS drag connection might look like. The point that I'd like to emphasize is that the engineer wanted to make it explicit that the filler metal that's used, or bolts, need to satisfy the requirements of AISC 341. And then here's the other connection that uses the gravity type moment frame connection, so it doesn't necessarily have doubler plates and things of that nature. Doesn't require the removal of backing bars and all those things, but does require the use of the filler metal that meets the Sharpie V-notch requirements. And again, the specifics of the detail are not so much the point as the fact that the engineer has tried to make it clear by not over-specifying things that things must satisfy 341, instead trying to target where those requirements are actually something that the project is going to require. What many engineers also do on their typical details for seismic systems is to try to produce typical details for the basic system that they're looking at, in this case a moment frame. Now the actual moment frame may be more than the 3 stories that are shown here, but this detail shows the basic requirements, and again allows you to show that information in a consistent way from project to project. It also allows you to use the frame elevations to talk about the specifics related to the project that you're working on at that point in time. So here, for example, are call-outs for typical details related to interior and exterior moment frame connections, the locations of typical column splices in the seismic force resisting system that would be shown on the elevation, or perhaps if you chose to use a column schedule. Information related to column bases and the anchor rods and things of that nature. Again, so that the fabricator, inspector, when looking at things, can focus on the information that is repetitive and then use the frame elevations to look at things that are different. And here's just some other information that could be shown. For example, the RBS dimension callout. I'll take a look and show you a schedule that provides actual dimensions and kind of what the philosophy is behind how those things can be developed. And then here's an example of what a project-specific frame elevation would look like, and this is where you provide the actual member sizes, any particular doubler plates, stiffeners, things of that nature, where the actual column splices are going to be located, and the base plate requirements that are specific to the project that you're actually looking at. In addition to things such as the connection requirements, Larry mentioned the idea of making sure that we have properly braced our frame members, for example. And so here's an example of a typical detail showing how lateral bracing is provided when the framing is both perpendicular and parallel to the seismic force resisting system. So when it's perpendicular, for example, the beams provide the bracing in accordance with the detail that would be referenced to a seismic specific requirement. When it's parallel, there might be kickers or something along those lines. Again, want to remind everyone that when you use typical details like this, you need to make sure that for your particular base spacing and the number of beams that you have, that the interval or the distance between the braces actually satisfies the requirements of AISC 341 with respect to both L sub B and L sub P. The idea of trying to identify the demand critical welds, as I talked about earlier, again can be, I think, simplified and shown in some typical details so that you don't have to show them over and over again on each individual detail. I think that that promotes consistency, and I think it also promotes careful thought as to where these things are actually required. So here is an example of how that might be done, and you can get a sense of just the number of different conditions that might apply to a given project. This is an example from a moment frame, but you'd have similar conditions in some cases for other seismic systems, but they also might have some unique requirements. So most, for example, would have a column to a base plate issue, but you may or may not have a beam to column flange at the top or bottom condition to worry about in a particular system. There is one thing I also want to mention. On this detail, for example, it shows that the weld between the web and the beam web and the column flange has been classified as demand critical, and that's consistent with AISC 341. But if this were a reduced beam section, AIS 358 does not mandate that that weld be classified as demand critical. So again, depending upon the specific system that you're looking at would determine which one would make the most sense or would be a requirement. In addition to the identification of demand critical welds, there's also the requirement that the drawings indicate where backing bars either must be removed or they can be left in place but need to be reinforced with a fillet. So for example, here at the bottom flange in a moment frame connection, it's required that the backing bar be removed and then a contour fillet be added to the bottom side after the backing bar is removed. On the other hand, here at, let's say, a column base plate, the backing bar is allowed to remain in place, but the weld, the fillet weld that's specified in AISC 341 is indicated. And you'll notice that the weld is between the backing bar and the base plate, not up in here between the backing bar and the column flange. And if you read 341, you'd see where that's invoked. In the case of a reduced beam section, you have to provide dimensions in order to let the fabricator know or the fabricator's engineer needs to figure out what those dimensions are so the shop knows what to do. And you can see here that on this project there are only two different groups of dimensions. And what many engineers will do is they will review their designs, try to select a reasonable number of different beam sizes, and then see to what extent those beam sizes can be grouped to use the same RBS dimensions and yet still satisfy the requirements of 358. And by doing that, again, we can simplify the information and promote consistency rather than have things change on every single frame girder. Now, sometimes it's not as easy to make that work, and you may end up with more than just the two that are shown on here. You also, as I said, need to make sure that you have still satisfy the requirements of 358 with the groupings that you use. In this case, you'll notice that the engineer has shown the A, B, and the C dimensions, and then has also shown the R dimension. If you go back and look at Larry's slide 47, I think it was, you'll see that R can be calculated by those three properties. Actually, you don't even need the A, but the engineer chose to provide that information. It's not really something that is required, but is something that they chose to provide. The other thing you'll notice is that the location of the protected zone, which is one of the required items that need to be shown on the drawings, is indicated here so that the fabricator and the subsequent subcontractors are aware of where the protected zone is, at least for the RBS connection. And then in this detail, there were some additional reminders, I guess, to the things that are related to the seismic requirements. That AWSD 1.8, there is a requirement for welders that are making the weld. Generally, it's the weld of the bottom flange of the frame beam to the column flange. Because they have to weld through the weld access hole and then stop and then start again on the other side, they have a restricted access in that area. And so there's a requirement that these welders pass a specific test in order to be able to perform those welds. And so the drawing reminds everyone that this is a requirement, although this is something that is specifically required in AWSD 1.8. Perhaps the engineer was concerned that it had been overlooked in the past. Also describes some of the things that need to be done when well tabs are removed, and that nothing is to be attached in the protected zones. The seismic provisions require that connection configurations be shown, and so here are some details that illustrate that. Again, referring to the specific system here. In the case of the moment frame, I have some other examples to talk about, particularly as it relates to brace frames. But it provides the fabricator with the basic information so that they understand how that connection is to be configured. Plate sizes and things like that that relate to specific requirements, those might be shown on your frame elevations, for example, such as the thickness of the doubler plate. But if a doubler plate is required, this is where that information might be shown. Here's similar conditions, except looking at it at the exterior of the frame, both at an interior or an intermediate level as well as at the top. And so in laying out these things, you need to give some thought as to the different conditions that need to be reflected in the details, and that showing just one moment frame detail sometimes might work, but it usually makes it easier and invites less confusion if the engineer has taken the time to show these things. And since these are generally typical details, the time spent in developing them can be leveraged on other projects. Here's an example of again, another connection geometry as it relates to the column splice. The reason for showing this one is to remind engineers that in section A4 of AISC 341, the engineer of record has to indicate where tapered transitions are to be located. And so this is the tapered transition here. The actual requirements for tapered transitions used to be specified in AWSD 1.1. Now the requirement is that in D1.1, tapered transitions are required where the engineer says they're required. And so AISC 341 provides quantitative guidance as to when the taper transitions are required, and AWSD 1.8 provides the detail that shows what this taper transition is to look like, although this particular project had a detail that provided the geometry specifically. Here's an example again of another connection configuration focusing on the doubler plate. Showing welding that would be required to attach the doubler plate to the column flange, both at the inside of the column flange along the top, and if necessary through the use of plug welds in order to deal with the plate and web slenderness requirements that are specified in 341. Here's an example of the bracing detail that might be required if the framing is parallel to your frame member or is perpendicular to your frame member. Example again of another connection geometry showing the doubler plate requirements. Again, as a typical detail that would be referenced from your larger frame elevations or your frame connection details, and then a look at the base plate itself. Now, there are some special moment frame beam to column connections that are proprietary. And when I use the word proprietary, what I mean is that there is a patent on the connection itself, and the owner of that patent will license others to be able to either use or fabricate that particular connection. And there are several that are proprietary that are listed in AISC 358. So what I want to do is just briefly show how many engineers deal with this particular issue. Generally, the engineer of record shows the frame configurations, in other words, where they are, the basic member sizes, and then delegates the connection design to the manufacturer or the holder of the patent. And then generally what happens is that the owner of the connection will provide details that are either incorporated into the drawings or treated as what we would call a deferred approval. In other words, they're listed on the either the structural or the general index sheet of the project drawings, and then serve as a separate submittal both to the engineer and, if required, to the building official. In terms of special concentrically braced frames or other brace frames, just show again a typical elevation. This is a nice simple one, only 2 stories or only 1 story tall, and it's simple in the sense that the gusset plate schedule lists again only one particular gusset plate geometry. And then through the use of typical details, the basic geometry of the gusset plate then can be understood by the fabricator when they have to construct this detail. Larry mentioned the requirement that the gusset plate details be drawn in such a way that they communicate where and or how and where inelastic deformation needs to be accommodated within the connection itself. And so this is an example of a special concentrically braced frame where the engineer has determined that the design intent is to allow the braces to buckle out of plane. And in doing that, it will create, and there are a variety of different terms that are used. I think Larry's slides use the term fold line. I think these details use the term bend line. Some people call it the buckling line, although I don't think that's probably the most accurate way of describing it. But the idea is that the engineer has tried to describe where that line needs to be. The idea is that this line needs to be free to bend without restriction, at least for this particular connection configuration. And in order to do that, because this gusset plate is stuck into concrete, let's say at the top of the footing in this particular case, or perhaps in a metal deck topped diaphragm, a compressible material is required around the gusset plate to allow it to be able to bend in and out of plane. If the compressible material had not been provided, this bend line or fold line would not be able to form in the geometry that the engineer of record assumed when they detailed and designed these particular connections. So you can see both in elevation and in plan, in this case I think it was 1.5 inches of compressible material. I think the detail uses the term styrofoam, but that's proprietary, so compressible material is probably a better term, and then that could be defined in your specifications. Again, the example of this connection where the braces intersect the beam, again, the line that is to be free to be able to bend and allow this brace to be able to buckle out of plane has been identified. Beam to column connection for a special concentrically braced frame. Again, in this case, different from what might be required for a moment frame, and so a specific detail would be provided for that particular configuration. Then the last basic thing that I'd like to talk about is another proprietary system. The beam column connections for special moment frames. There are some proprietary connections. Here, the basic element that makes a buckling restrained braced frame, that's the BRBF, those are proprietary. And so again, the engineer of record has to convey enough information so that the design can be understood by the fabricator or the contractor bidding on the project, as well as by the building department to make sure that the design satisfies the requirements of the building code. So generally, the engineer of record will show the configuration and the basic brace properties. I'll show those on the next slide. And then the engineer of record delegates the brace and the connection design, because the connection design is a function usually of the brace itself. There are sometimes choices in basic geometry that the engineer of record, in conjunction with the architect, might make, but that's what the basic information is. And then through a schedule, the requirements for showing the strength of the brace is really the only thing that has to be shown to communicate that information to the brace manufacturer, as well as a stiffness modifier that would be required to calculate the performance and drift of the brace frame system. And this is something that would be determined by the brace manufacturer, but normally would also have to be shown on the drawings, at least initially, and then confirmed in order to get your design through the building department. And then the brace manufacturer would provide the details and a detailed schedule of things related to the brace itself. And then the last thing is that there's a requirement that the connection between the concrete floor diaphragm and the steel seismic force resisting elements need to be shown, and in this case this is being done through the use of the shear studs, and the number of studs are shown on the plan, and the details here show how those would be located within the deck itself. And so that finishes the my portion of the presentation. I'll turn it back over to Christina.
All right, thank you, Tom. It looks like we have time for a few questions. For the first question, I'm going to take us back to slide 35. And this is a question for Larry. Could you explain what a demand critical weld is?
Yeah, so just very briefly, a demand critical weld, there's a couple ways to look at it. So the reason we have demand critical welds is discussed in the commentary, I think to chapter D, I believe, and it talks about the inelastic demand, the high stresses and inelastic demand on these connections. So that's kind of why they're required. When are they required? They're required when listed in the specification or by the engineer of record. And then from a performance standpoint, what exactly is a demand critical weld ultimately in the field? It'd be best to look at AWS D 1.8, and it provides all of the requirements, most of which pertain more to the welder, to the contractor, than they do to what the engineer necessarily be interested in directly, but that defines the requirements.
Okay, thank you, Larry. For our next question, I'll take us to slide 56. This question is for Tom. Are seismic design parameters required to be shown on the drawings if we are in design category A or B, where seismic detailing is not required?
Well, seismic design category A has no seismic requirement, and so no, you wouldn't have to show it. In seismic design category B, it says that the seismic parameters are supposed to be shown even if seismic design does not govern. They have a similar requirement for showing the basic wind speeds, for example.
Okay, thank you. Next question, I'm going to take us to slide 46 for Larry's usual suspects. You discussed the first point on here is that no pre-qualified connections are allowed to the weak axis of a column. The question is, can moment connections be made to the web of a column if the frame in that particular direction is not intended to be part of the seismic force resisting system?
So the brief answer is yes. So if you have a moment connection to a column web, and the column web is not part of the seismic force resisting system, it's not part of that special moment frame or intermediate moment frame, then you don't have to meet AISC 358. So one common case would be if you have a cantilever that's just simply resisting gravity loads. The only sort of caveat to that is you can run into issues if you put something in the frame, a moment frame for instance, that could take seismic load, but you make the assumption that it's not. You have to be able to justify that assumption as well.
Okay, thank you. And another question for you, Larry. On slide 19, what are the units on the left side of this graph?
They're intentionally left undefined. The graph's just supposed to be almost pictorial. Like I said in the presentation, it's a rough representation. I don't want anybody reading too much into it, so I've just left things undefined.
Okay. And also, Larry, could you explain a little further when we can provide a contouring fillet to a backer bar versus when we are required to remove the backer bar?
So again, this is the best place to look is to go to AISC 341 and do a search for backing, and it'll tell you exactly when that needs to happen. You'd also, if you have a pre-qualified connection that you're using, go into that document and look under whatever configuration you've chosen. But generally, the idea is that you can allow the backing to remain and provide the reinforcing fillet if you're to the inside of a section. So when you go to column base plate connections, it talks about if your backing is to the inside of the section, then you can leave the backing and provide that reinforcing fillet. If you're at the top flange of a beam, you're assuming that both those CJP welds are being made from the top of the beam. So at the top flange, you're to the inside of the section. You can leave the backing in place and provide the contouring fillet. If you're on the bottom flange, it's to the outside of the section. So we require you to remove that backing and then either provide another fillet there, or to contour it, or to grind it. And then just a couple other clarifications on this. One is you're always permitted to remove backing. So if you choose that as a better option for some reason than leaving the backing and providing the fillet, that's okay as well. I think that'd be unusual to do. The other thing, in our review session, somebody brought up the fact that people get confused about removing backing sometimes because they confuse backing with weld tabs, like run-out tabs on the edges of CJP welds. And so those are very different things. So even when you have to remove a tab, you could still potentially leave the backing in place.
Okay, thank you. Unfortunately, that's all the time we have today for questions. If your question did not get answered, we will reach you by email with a response.